Hello, thank you, Michael. Thanks for everybody for coming. So I've been giving what Paul Erdős would have called PGOM lectures, poor great old man lectures, at a workshop on a subject I sort of started on strong stationary times. And we there's some people who came, so we study convergence of a chain after L steps from to stationarity in various senses to pi of y as L goes to infinity by finding a stopping time t on as the chain progresses such that the chain at time t is exactly distributed as pi, and such that the chain stopped at time t is independent of t. Such a thing is called a strong stationary time. And in my first lecture, I just define these things, and we prove that the distance of KL total variation was less than or equal to the separation distance after L steps was less than or equal to the probability that the stopping time is bigger than L. And so you can study convergence by studying how long it takes to get absorbed. And the main thing I did in the first lecture was to do 3 examples. I did top to random. I did random walk on the hypercube. And I did riffle shuffling. In which we actually built these strong stationary times with bare hands. And I had one other example I wanted to do, and so I'm going to do it. And one reason for doing it, was to remind you, you can actually find them and do it, and not just talk about it. Okay, and so I want to do one more example, which is random transpositions. And that example said in English is the following. You have a deck of cards labeled 1 up to n, and they're all in a row on the table. And there's card 1, card 2 up to card n. And the dynamics are you pick a card at random with your left hand, and you pick a card at random with your right hand, and you switch the 2 cards. You just do random, and your left hand is allowed to equal your right hand. Otherwise, you have a parity problem after an even number of switches. You're at an even permutation. So that's random transpositions, right? And one reason for talking about it is the first Markov chain where cutoff was proved on work I did with Shashahani. So suppose we did it by Fourier analysis, but suppose I want to do it by thinking. Okay, just make a strong stationary time. So you'll understand this. Here comes. I'm just going to do it in the air, but you'll all understand it. So there are the cards, and they're in order, right? So I'll write it down in case you want to write it down. So you pick 2 cards at random. The first step, check the first 2 cards. Chosen. Okay, so they might only be 1 card, in which case you check that. So the first 2 cards you touch, you switch them, and then you make a check mark with a pen on the back of them. Okay, that's the first thing. And then as you are switching cards, if you hit check card, and an unchecked card, check the unchecked card. So, okay. And you can think that makes perfect sense. At the start, there's two random cards and they're checked. And then as time goes on, the check cards are a random subset of the cards. And when you add an unchecked card, you check it, it's also a random card. And also this helps if both hands hit an unchecked card. Check it. Okay, so you can see eventually, of course, you'll check all the cards and let T be the first time. All are checked. That'll happen eventually. And bounding the tail of T is easy, right? It's a coupon collector's problem. You're adding to the unchecked card, and that's a strong stationary time. T is a strong stationary time. So of course you have to think through that argument, and it's easy to make mistakes. If you want to see details, I did them in my book, but a better thing to do is look at this paper on the archive by my student Graham White, XIV. I'll just write the archive number if I can find it, 1910.00770 is a good place to read that argument. This argument this proves sep L is less than or equal to e to the minus c when L is equal to n log n plus c. And I mean, that's the coupon collector's problem. And Graham gave a modification of it, which managed to do total variation, got the half. So for total variation, it's a factor of 2 faster, half n log n plus c. Suffice to make, here's a theorem. If L is that, K XL minus uniform distribution is less than or equal to 2 e to the minus c. And in fact, we know the shape. If you take this many steps and you look at how this behaves as a function of c, Lucas Tessier knows the shape, and that uses very refined character estimates, but you can get this with some bound of this sort from strong stationary times. So it's just to remind you, you can actually find them and think about them. And okay, so that was the first lecture I gave. In lecture 2, we talked about cutoff. We talked about birth and death chains, and talked about the Perez conjecture, the product conjecture. And I used duality to represent the dual of a birth and death chain as a birth and death chain, and then you could prove proof using duality for birth and death chains. So that was lecture 2, and probably they'll all be in the movies, and they're all online. In lecture 3, we defined and constructed strong stationary duals. If X is the process, we constructed an X star process in another space in various ways, set value duals, and we used monotonicity. To make it neater and better. And one of the key technical ingredients was this notion of if there was a link, if lambda from the dual space to X space is a link function, and then if I have my star chain xn minus 1 by k star into xn, and I had xn minus 1 into xn by the k chain, and here is the link function. These are two Markov chains, and there's this link function. We constructed Markovian process, joint Markovian process X star, such that I don't know, it marginally was X and X star. The two margins are right, and then the law of Xn given X0 up to Xn star equals little equals something. Equals little xn star is equal to this link xn star. So this diagram commuted such that xn minus 1 star is conditionally independent of given xn minus 1 of xn. So this and this are a Markov chain. That's what this says. And the other way too, xn minus 1 star was conditionally independent given xn star of xn. So go this way is a Markov chain. So that was a kind of, not by me, but people seem to call that the Diaconis fill construction, and it seems to be useful. So that's where we've been, and what I want to do today is the following. So suppose you were a graduate student or a young person, or maybe even not such a young person, and you said, I want to work on that stuff. Is there something I could do? Is there a good paper to take to the future? And if I told you some problems to work on, some papers to read, this is what I would tell. So I'm going to tell it to you now. Okay. And I have a handout. I hope everybody has a handout. If not, there is a stack of them, and I can give you one afterward. And so the references are on that. And let's go through a little ways, and then I'll tell you what's new, because I think there are some things that maybe you haven't seen, where people are using what I just talked about in order to do new things, and it's alive and wonderful. If you aren't so familiar with Markov chain theory and you wanted to background, the best possible book, I think, is the book by David Levin and Yuval Perez, Mixing Time and Markov Chains. It's free on David Levin's homepage. That's maybe useful. The lectures I'm giving are based, as I said at the start, on two papers, one with Aldous and the American Math Monthly, which is friendly. That's the first one to look at. It has these kinds of examples, lots more that I haven't told you about. And then the paper with Phil, which is less friendly, but okay. If you wanted to see lots of examples of constructions of the type I just did, because that's the way to learn, is to see examples. I think that's the way to learn. If you want to see lots of examples of constructions of strong stationary times for Markov chains which don't have uniform station, not random walk on the group, I mean some other Markov chain. Igor Pak's thesis is pretty good. Even though it's called a random walk on groups, it's got lots of non-group examples, and it's Igor Pak's on his website, and he's a professor at UCLA. For the Perez conjecture, it's work I did with Solovkost, and then there's a beautiful extensions doing it for trees using different methods, in particular by Basu, Herman, and Perez. And the state of the art about the Perez conjecture, the product rule, is work by Justin Salez, and his paper Cutoff for Non-Negatively Curved Markov Chains is a very good way to find the literature. I talked about, and I will talk about at the very end again, this set of problems and theorems about what do most Markov chains behave like? Well, okay, I did most birth and death chains with a given stationary distribution, and I'll come back and talk to you about that. But the references are here, and then Laurent got interested in trying the arguments are often quite analytic, complex variables type math, and Laurent got interested in trying to prove some of those theorems using duality, and his and my efforts are also recorded here. So that's the first thing I would tell the student in the first meeting. Okay, go look at some of this literature. It depends where you're starting and what you want to, where you want to get to. One of the people who has been actively using this construction of this construction of a bivariate chain from two marginal chains and a link is Yuval Perez. And let me tell you a little bit about what he's doing and why he's doing it. And so this is not a detailed lecture on that subject. I'll tell you enough so that you can see if you want to go look at it. And there's a reference to it. That's the best I can do. As you'll see, it's a healthy development, and there's no possibility of doing it even in an hour. But one of the starts is this thing that's called the evolving. So Ben Morris and Perez, evolving sets process. And so we're on a, say, finite state space with a Markov chain, kxy. It'll be reversible with reversing measure pi. We run Markov chains based on that. They make a set-valued process. And I'll just tell you one step. It's a Markov process on subsets. If S is a subset of the state space, the next step S prime, the next step in the chain, is equal to the set of all y, such that in one step you can get from S to y is bigger than or equal to u, where u is uniform on 0, 1. So at each step, you pick independently a uniform, and you're at S, and you look at the set of all y's such that you can get from S to y. The chance of doing that is bigger than u. That's some set of y's, right? That's some set of y's. And of course, it could be empty. It's possible it's empty, in which case the process is absorbed. And so that's the evolving sets process. Okay, it's a little, oh, I forgot pi, pi of y. Right. So when somebody just writes that down, we say, well, if you say so, you know, that looks a little bit funny. They developed it, Ben Morris's thesis, they developed it in order to give a probabilistic proof and interpretation and sharpening of Cheeger's inequality. I'm not going to talk about Cheeger's inequality, but that's the conductance bound that Cheeger did for the Laplacian on manifolds, bound on the second eigenvalue with the Laplace operator on a manifold, and then we in probability have used conductance bounds all the time, but it's quite analytic and not so probabilistic. And they gave a very, very nice development of Cheeger's inequality with real sharpenings and using these evolving sets. And if you want to see that lovingly and friendlily described, look at chapter 17 of Yuval, of the Levin Perez book. That's much better than the Annals paper. The Annals paper was hard, so this evolving set process has many properties, and I'm not going to tell you about very much, but facts that are crucial is if you look at the stationary probability applied to S, so I'll call it process at time L. Start at S naught is equal to a point, and look at the set valued process. This is a martingale. This is a martingale, and that's useful. What else do I want to tell you about it? There are a lot of things to say. For example, and these are all elementary, and the chance of going from the original chain from X to Y in L steps is equal to pi of Y over pi of X times the chance of going from the set X to the set of all so the chance that the set valued process started at X covers Y at time L, normalized that way, that's equal to this. And so you say, oh, it's connected. It's kind of something to understand. And there is something to understand in its beautiful probability. And I'm not gonna develop it. But what's the connection with me, with this conference? And that connection is developed in Yuval's book in particular, and in many papers, maybe 10 of them by Yuval as time goes on. What he did was, this is a Markov chain. Right? The set valued process is a Markov chain. We have another Markov chain. We have K. I have a way of sticking two Markov chains together, right? I could do it to that construction, right? I could take the set valued dual, the set valued process, and I could take the original Markov chain and do that to them. Okay, and so they make an XL-SL process with these rules with the probability that XL is contained in SL equals 1. So they couple the two processes together using this construction with fill and so first of all, at least you understand what I just said, right? That is, I've got my original chain, I've got this set valued process, and then we've got this way of sticking two processes together, okay? You do, it's true. You have to do transform it, not to be absorbed. That's true, that's true. And okay, that process is at the heart of 10 papers of Yuval Paris. And now I'm not going to tell you about 10 papers of Yuval Paris, but I'm going to tell you about one of them, which is one of his two patents. He was head of Microsoft Research for a long time. And you can, so that's the reference, 6 or someplace there. This is finding sparse cuts locally using evolving sets, and that's on the archive, but it's also a long paper with Luca Trevisan, and they use that to find communities. He was at Microsoft. Microsoft is interested in the web. They were running this set-valued process on the graph of the internet, and the sets that it concentrates on seem to be very good at finding sparse cuts, at finding sets which contain a given person or community and have small connectivity to the outside world. And I'm not going to explain that further, but Yuval sent me a movie, and it's from his paper. And so if I was a modern person, I could have asked Michael to show the movie, but you can all picture there's a graph of the internet and there's a set evolving, and okay, so pretend you just saw a movie, but you can click on your phone and see it too. And you can look at his paper. It won all kinds of prizes. So the use of this construction, the point is, because the Markov chain is the nearest neighbor random walk on the internet graph, if you're at a user, you can look at all the people who are connected to him. You can actually do it instead of talking about it, and then this set will grow. And the set is useful and had provable properties. So that's an example of an application of this machinery to machine learning, and it seems to have been a big deal. More mathematically, and I know we're going to hear more about this next week, those of us who are here, but this construction of this paired Markov chain was the construction is crucial to a series of 8 or 9 papers by Yuval and many co-authors, ones he's doing just now, for doing the behavior of random walk on evolving percolation clusters. So you take percolation, say, slightly above criticality on a lattice in ZD. So you've got this random graph. You erase edges with probability P and leave them in with probability 1 minus P or whatever it is you do. But, and you do random walk on that. Every once in a while, every edge has a Poisson clock, the edges disappear or reappear. Okay, so the graph changes. Now, of course, graphs do change, right? The internet really does change. And so he and his community are interested in how does our intuition and our theorems about random walk on a lattice, for example, there's been enormous, random walk on an Erdős-Rényi graph at the criticality. Been enormous work of random geometries. Well, suppose the geometry evolves, as geometries do evolve. What can you say? You really have something to say, and all of it uses this construction. Now, remember, you're a graduate student or a new youngster. That's you. Sorry. I'm saying you should look at these papers, and I put down the name of the papers. That's all I'm going to do for you, right? I'm just trying to sell you looking at a paper and saying what it's about. That's all I'm trying to do. It's a healthy, very current. The papers are just appearing on the internet now. He's been doing it for the last few years. The results are interesting. There are lots of open problems. The machine he's using it for is useful much more generally. It's useful for time inhomogeneous Markov chains with the same stationary distribution. You can understand, at each time you maybe change the kernel. It depends on time, but the stationary distribution is the same. And how can you analyze chains of that sort? And this gives you a way of doing that. It's interesting, and every one of the papers has 10 pages on the oldest, not on the Diaconis fill thing. So, okay, since you now know what it is, I'll erase it. Okay, so that's a first place for my erstwhile hardworking graduate student to look at. Much more, much broader, much deeper, I think, is the work of Alexei Borodin and Vadim Goran and that crowd, Michael Wheeler, I'll write Borodin et al., because there are a lot of people in that crowd et al. Work on integrable systems. And here comes systems. Okay. Here comes alphabet soup. There's TASAP. There's ASAP. There's PushSAP. No kidding. There's random matrix theory, the Dyson's Brownian motion, and there's KPZ. There's this world of these letters, and everybody in this room has probably been exposed to some of these letters at some stage in their life, and Borodin is, so if you get nothing else from my lectures, right, there are 4 of them, if you get nothing else, look at this thing that I talk about. I hope I wrote it down. Yeah, here it is. Look at this is in item 7. It's lectures that Alexei and Vadim Goran gave, and they're on the archive. They're in item 7. They're not very long. They're beautifully done. It's about 50 pages. You can follow them. I'm going to give them to you in 10 minutes. Okay, so you see whether you think you could follow them or not. And everything I'm aiming at, the applications of duality to integrable systems, is sketched out in those lectures with full references and lots of pictures. And Alexei's lectures are on the internet. They're YouTube videos, so you could look at them. But look at this paper, okay? That's you're a working young person. Go read that paper. So what do I want to tell you about it? Okay, so just to start, so here's a start of description of how they use duality for integrable systems. So let P of n be all partitions of n. of n. So for example, P of 5 is equal to, well, 5, 4, 1, 3, 2, 3, 1 squared, 2, 1 cubed, and 1 to the 5th. So there's 1, 2, 3, 4. Oop, I'm missing one. What am I missing? 3, 2, 2. I should have put it in anyway. Here it comes. 2, 2, 1. There's 7 partitions of 4. 5, 5. There's 7 partitions of 5. Is that okay? That is, I write a partition if I write lambda as a partition of n, lambda 1 bigger than or equal to lambda 2, bigger than or equal to lambda L, where summation of bigger than 0, summation of lambda I is equal to n. And I often will write lambda is equal to the product of I to the AI of lambda if lambda has AI parts, size I. So I hope that's familiar or clear at any rate. And there's a world of literature, I mean a large world of literature, larger than anything in this room, of this kind of thing, enumerative theory of partitions, Ramanujan, but I'll say it in our language, pick lambda contained in Pn at random. What does it look like? That's not a math statement, but you know, how many singletons does it have? What's the size of the biggest part? How many parts does it have? Blah, 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 right? It's a huge subject, the enumerative theory of partitions, George Andrews' book. It's a huge subject. Well, what do I mean by at random? Here are 3 measures on P of n. That are used. One is the uniform distribution. That's a way of picking a partition at random. Second is 1 over z lambda, where z lambda is the product of I equals 1 to n of I to the AI times AI factorial. You have to check, you know, that these numbers add up to 1. But what is it? Where do they come from? This is if you pick sigma, a permutation in Sn uniformly, and report what conjugacy class it's in. Report the class, the conjugacy class. You know, the conjugacy classes are indexed by partitions, and the chance that you have the partition lambda is 1 over z lambda. That is the group acts transitively on conjugacy classes, and the size of a class is the size of the group divided by the size of the isotropy subgroup. The size of the isotropy subgroup is that, and the size of the group is n. And since I'm picking uniformly, the n factorials cancel out. Anyway, that's a measure on partitions. A very popular one is the probability of lambda is equal to f lambda squared over n factorial. It's called the Plancherel measure. F lambda is the dimension of the irreducible representation of the symmetric group. Corresponding is given by a formula, but and these numbers add up to 1, and that's a very important measure on partitions. And there are lots of others. Okay, there's lots of measures on partitions that people use, and then ask these kinds of questions. Well, here, in order to describe the measures that are important for Borodin and company, I have to remind you about symmetric function theory. So I teach a 10-week course on symmetric function theory, and But okay, so symmetric functions. A polynomial p of x1 up to xk is symmetric. If it's invariant under permuting coordinates, invariant under Sn, Sk. So everybody knows, for example, e.g., the power sums Pj of x1 up to xk is just equal to the sum I equals 1 up to k of xi to the j. So the power sums are familiar, and then products of power sums are symmetric functions, and they form a basis for the ring of symmetric polynomials, the power sum basis. Everybody also knows the elementary symmetric functions, another famous basis. E0 is 1, E1 is summation xi, E2 is summation xi times xj, I less than j, and El is equal to summation xi1 times xi2 times xi where 1 less than or equal to I1 less than I2 less than IL. So these are, you've all seen the elementary symmetric functions someplace in your life, and products of elementary symmetric functions are a basis for the ring of symmetric functions. And so there's a bunch of bases. There are lots of them, actually. And but there's a magic basis, which are called Schur functions. And they're, I'm just going to say they're a magic basis. They're called S lambda of x1 up to, I don't know, however many variables I'm working with, where lambda is a partition of n, for example. That'd be a basis function of dimension n. And I can certainly define them for you. They're not easy, they're not very hard to define, but it's hard to define in a motivated way. It's famous that nobody can define them except one thing that maybe makes them more natural for some people is the characters of the unitary group. I mean, that's a fact. I mean, that is, the unitary group is a natural group. It's a compact group. The ordinary unitary group, UN, n by n matrices with matrix star is the identity. That's a compact group. It has characters. The characters are polynomials and the eigenvalues of the matrix, and those characters are exactly the Schur polynomials. That's one way of saying it. They're given by a determinant formula. They're given by sum over Young tableau. So and so that's another basis, and that's going to be important for us. So a specialization, and I'm going to T this is the ring of all symmetric polynomials in, say, M variables, all symmetric polynomials of all degrees in M variables. A specialization is a map into, say, R, which is an algebra map, such that the specialization applied to the sum is the sum of the specializations, and the specialization applied to the product is the product of the specializations. Okay, so it's an algebra map. And so, for example, you could just set the variables equal to numbers. So that's a specialization. There are others, and we know what all of them are. That's Thomas' theorem, but It doesn't matter. And I'm going to write S lambda of rho, where rho is going to be a vector of m numbers. Those aren't the only specializations, but those are a lot of specializations for this specialization. But I could write it S lambda of T sub rho, and a specialization, so we know all of the specializations. So if this is bigger than or equal to 0 for all lambda, that's called a positive specialization. The specialization is positive. So it's elementary to say, but in particular, I could set all of the variables to positive numbers. That's okay. That is, if I set all of these xi's to be positive numbers, the elementaries are positive, right? So it's the same for the Schur functions. That is, there's a combinatorial definition of Schur functions. Okay, so now I have some positive number for every lambda. If you're a probabilist, it's not so far away. So definition, remember I was saying different distributions. This is due to Okunkov, Breshetikin, but a Schur measure on the union of Pn for all n. So all polynomials, partitions. Schur measure is P of lambda is equal to S rho times S rho prime over a normalizing constant lambda rho prime, where rho and rho prime are positive specializations. And this is a normalizing constant which H rho prime is equal to e to the sum from k equals 1 to infinity of p k of rho pk of rho prime. These are the power sums divided by k in the exponent. That's what the normalizing constant is. So this is a positive number. And so for each partition of lambda, I have a positive number. This makes them all add up to 1. You have to assume a little something about the rows, that you have to assume that one of these sums is finite, but that's okay. And so these are called Schur measures. So they're measures on partitions, and if you see them, if you're you and you haven't seen anything like this before, you think, what are they doing? This is crazy. It's not crazy at all. It's amazing math. Let me make a connection, one of the many theorems that Okunkov proved about Schur measures. So we draw partitions 3, 2, 2, 1. We draw them, I draw them this way, 3 boxes, 2 boxes, 2 boxes, and 1 box, which pk is the power sum. Yeah, right. You have a specialization, so it makes sense to apply it, right? Thank you. Right. So we often draw partitions as Young diagrams, that's just dots, that everybody's seen. That's a way of graphing partitions. So the Russian way of graphing partitions is not this way. This is English style. French style is they do it from the bottom up. The Russian style, they turn it 135 degrees. I'm not going to do that, but I mean, I want to turn this so that this thing is I want to turn this 135 degrees, so that, it goes. All right. I don't know. There's got to be a partition, so. Anyway, take a Young diagram and turn it 135 degrees. You can all do that better than I can, right? And now take all of this jaggedy path here. Suppose this went this way. Take all of the down points project them down. So you have a partition, you rotate it, take all of the local minima in the upper edge and project them down onto the x-axis. That's a point, those are points on the x-axis. Right? And if the partition's random, they're random points. It's a point process. Aha, point process. For any sure measure, for any specialization, the point process that you get by the Russian construction of partitions is a determinantal point process. So theorem, that's the theorem of Okunkov's. So theorem, the projected points, minimum points, local minima points onto the x-axis form determinantal point process. Now, so that's another subject. Symmetric function theory, that's a subject. Determinantal point processes, that's a subject. Sorry, guys, but it's another subject. So let me just say a sentence about that subject. So a point process on an arbitrary space, these are things that physicists do. Dyson is the first one that I knew about it, and that's the start of random matrix theory, but they were abstracted by a wonderful lady named Machi, and that's a huge subject. Point process is determinantal. If the probability that you have points I'll do it discretely. These are discrete point processes at points at I1, I2 up to IK, and maybe some other points, but at least points that the random point process contains points I1 up to IK is equal to the determinant of a kernel K I A I B for 1 less than or equal to I A IB less than or equal to K. So if the chance that you have points at a given set of points is given by the determinant of a certain kernel, and the kernel well, it doesn't matter. There's an explicit kernel I wrote it down, okay, won't help anybody. So this all sounds okay if they're doing it. So a very special case, fix Q 0 less than Q less than 1, and take rho, the specialization, to be Q and 0, all set set one of the variables equal to q, and all of the other variables to 0, then the Schur measure, the Schur measure p rho q of lambda is a Poissonized Plancherel measure, is equal to e to the minus q squared times q to the size of lambda times times the dimension of lambda over the size of lambda factorial squared. So this is the Poissonized, that is, pick n from a Poisson distribution and then pick a partition of n from the Plancherel measure, and it's what you have to do in order to prove and understand, because we know about determinable point process. This gave Okunkov's proof of the Bike-Steiff-Johansen theorem. A fairly conceptual proof, namely that the probability in Sn that the length of the longest increasing subsequence in a random permutation minus 2 root n over n to the 1/6 less than or equal to x converges to the Tracy to f, f sub Tracy of x. So this machinery, in the most trivial special case, the specialization was just one variable, but having all of the machinery available gave a kind of neat. So all of this is in these lecture notes of Goran and Alexei. So let me, because time is about over, let me at least say what it has to do with the construction I did with Jim Phil. And then what's so exciting, you can make Markov chains on partitions, and where did I write those down? There, someplace. Two Markov chains on all partitions. The up chain, lambda goes to mu, and it depends on two specializations, positive specializations, and there's some formula, S rho sub mu divided by H rho prime, that normalizing constant, times S lambda sub mu times S, and I'm sorry about this, but mu minus lambda, so a skew-Schur function at rho prime. But these are parameters. This is the chance in one step of the Markov chain of going from the partition lambda to the partition mu. And these are all specializations of Schur measures. And this thing, if you sum it in mu, sums to 1. And then there's a down chain, P lambda to mu going down, rho prime, and it's some other formula. Okay, so there are two Markov chains on partitions given by these specializations. Well, I have two Markov chains. I have a way of sticking them together. Right? That's what I've been talking about. That's what Alexei did. I was there when he did it. I was visiting at Nice. Laurent was around the corner. He said, is there a way of sticking together two Markov chains if you have some kind of projection? And I said, yes. And it's the stuff I did with Phil. You can stick these two Markov chains together and make a bivariate chain, and then you can make multivariate chains. I'm not going to do anything more than just tell you they made a process which looks like this. Lambda K1, lambda K2, these are, say, less than or equal to lambda K. K, it's a Gelfand-Zetlin pattern, lambda K minus 1, 1. This number is in between these two, lambda K minus 1, 2, lambda K minus 1, K minus 1, and on down to lambda, 1, 1. So he made, he stuck these Schur processes together and made longer ones, and these numbers in the top, so, and this is a process, it evolves as arrays of this sort. This is a process on Gelfand-Zetlin type arrays. This top row, if K is large, becomes, converges to Dyson's Brownian motion, to the eigenvalues of random matrices. And this row, these are integers, which are going down, converges to Tay-Sap. Okay, that is, it's where the particles are in Tay-Sap. And as far as Alexei's, because why does KPZ asymptotics apply both to random matrix theory and to Tay-Sap? That's his best explanation. Okay, that is, this is a joint distribution which unifies. Now, I just told you much too much for anybody to take in, but maybe you have some idea of what I just said. If you want to look at it, it's 40 pages of lecture notes. They're beautifully written, and I'm trying to sell it to you. You remember, you're a beginning graduate student, right? Or a serious beginning graduate student, otherwise. Okay, last, I'm not gonna, last thing to say. So this is a beautiful development. It goes on and on. It's very deep, it's very broad, and right in the middle of it is this, this construction of dual Markov processes, and written large and used, and all the kind of properties that we've been talking about. So if you want to look, take a look. What I really hope people would do is, I guess if you're in the math department, you think, I've got to make stuff that nobody can understand, like what I just told you about, right? If you're not in my part of the world. This is bread and butter for me, but probably for most of you, it's Martian language. What I hope people will do, instead of working on this, is take an actual Markov chain that some scientist, biologist, physicist, statistician is running, and try to prove anything about it. There aren't enough people doing that. People are making abstract theories and not doing examples. The most exciting thing to do is link to what these guys are doing, these three guys here. If you want to know what Markov chains are people actually doing, you know, tens of thousands of times a day. There's a suite of programs that is funded by Jim Simons at the Flatiron Institute, and the suite of programs is called STAN, S-T-A-N, and that's what all statisticians use, and many people to do their simulations. The Markov chains that are being run are Hamiltonian Monte Carlo, something called the no U-turn sampler, and then something called Riemannian Monte Carlo. So people who aren't, see, I'm afraid of Riemannian anything, but you guys aren't. Well, you're a little afraid of it, but somebody who's not afraid of Riemannian and likes Markov chain could probably prove something about those algorithms. People are actually using them, and they're interesting. And that would be a wonderful thing to do. And of course, finding strong stationary times would be a good way to do it. Doing it anyway, you know, prove anything. Okay, thanks everybody.
Okay, with this no further question, let us give a big round of applause to Professor Diaconis for his 4 lectures this week.
I applaud you for sitting there.